Hi, and welcome back. So, over the past few videos, we've been going over these different types of discontinuities we can have. And I'm just going to go ahead and write down the types of discontinuities that we've seen. So, the first kind that we saw was we saw the infinite discontinuity. So, infinite. And this is actually also sometimes, I know in my class we always referred to that as an infinite discontinuity. Sometimes it's also called the asymptotic discontinuity. And hopefully that it's kind of obvious why it could be called that, because it involves asymptotes. It involves functions that have some type of asymptote at some area. So in the example we saw a function, and I'll just draw it down here, where it got really, really close to the y-axis at x was equal to 0 from both directions. And that was the function f of x is equal to 1 over x squared. It asymptoted at this point. It asymptoted along the y-axis. And we call that an infinite discontinuity. Sometimes, or in your class, if you are going to take calculus, which you absolutely don't need to be taking calculus to understand these videos, I guess. But in your class, you might hear these referred to as asymptotic discontinuities. They're the same exact thing. So anyway, that was the first type of discontinuity we had. And actually, I'm going to just go ahead and erase this down here. Get my graph all cleaned up. Okay, so that was the first type of discontinuity. And then the second type of discontinuity that we had was called the removable, or sometimes called the point discontinuity. I've always known this as the removable discontinuity. But that was when we had a function, some function that was going on, and then there was just one point that wasn't defined on the function. Or maybe there was one point that was defined on the function, but it wasn't defined where the limit of the function was defined. So either way, in this situation, this was going to be a removable discontinuity. And if you remember from the end of the video last time, really most of the limit examples we are going to see when we start doing limit problems are really going to fall under these two categories. They're going to be either infinite discontinuities or removable discontinuities. But in this video, what I want to go over is the last type of discontinuity, and I'm actually going to just write this down here. And this is going to be called the jump discontinuity. And this is the last type of discontinuity that we have to go over. So actually, I am going to move my screen down there like that. And first, to start off with, I'm just going to draw sort of the intuitive definition of what a jump discontinuity is going to look like. And what this is going to be is it's going to look like if we have a function that's continuous and the function is moving along, and then say it's actually, let's say it goes down to that point right there, and it's undefined right there at that point, but the function jumps up somewhere else, let's say, and it could be either defined there, or it could also be undefined there, and then it keeps going. So this is going to be essentially what a jump discontinuity is going to look like. Some function is going to be going along, it's going to be undefined at some point, and then it's going to be defined somewhere else and then keep going. So anyway, let me actually give you an example of a function that would look like this. And actually I'm just going to get rid of all of those. And let me give you an example. Let's say we had a function f of x, and and normally when you deal with jump discontinuities, the functions are that you're going to deal with, if you're dealing with specific functions like we're about to do, they're really going to be these functions that are defined as piecewise functions. So I'm going to go ahead and define a function like this. And we're going to say that for x, okay, let's say, how about that our function f of x is going to be equal to x squared, and that's going to be equal to x squared on the interval minus infinity is less than x, is less than 0. So for all x in between 0 and infinity, and it's also in between up to but not including 0, we're going to say that our function is going to be x squared. And then we're going to say for all x bigger than 0 and bigger than or equal to 0, how about? We're going to say that our function is going to be, let's say, x plus 2. So let's go ahead and we'll start graphing this function. So right now, this is, hopefully we know so far that this is going to be a parabola. And it's going to be only this left side of our x squared parabola, right? So we're going to have a point at negative 1, comma 1. And we're going to have another point right here at negative 2, comma 4. So we're going to have these 2 points, and I still haven't gotten much better at drawing these parabolas. My computer just freaked out for a second. That's a really sorry looking parabola, I think, but hopefully you get the point. And then we're going to have an open circle down there. So that's going to be this x squared part of the function. And then for the second part of the function, we're going to define it as the line x plus 2, and I meant to write the limits down again, for 0 is less than or equal to x, and x is going to be less than positive infinity. So for all numbers larger than or equal to 0, we're going to have this line that has a y-intercept at 0, comma 2. So let's go ahead and put that point in. And then it's just going to be a line starting at that point with a slope of positive 1. So it's going to look something like that. So this is going to be the graph of our function. And so hopefully you can see that at this point, at the point 0, at the point x is equal to 0, we have got a jump discontinuity. Our function comes down and it approaches some point. We stop going along that graph. We jump somewhere else, and then we keep going. And this should, hopefully you can obviously see that this obviously fits our intuitive definition of continuity. We would not be able to draw this function without picking the pencil up and then moving it somewhere else and starting again. We can't draw this in just sort of one swoop of the pen, I guess. So it fits with our intuitive definition. Let's actually just go ahead and check and see if it fits with the I guess, rigorous definition of continuity. So let's go ahead and we are going to check the limit as x approaches 0 from the negative side of our function, f of x. And we can see as we choose values of x that are really close to 0, but just a little bit less than 0, this function is going to approach 0 if we're only looking at these yellow values for the function over here. So this side of the function is going to be 0. But then if we take the limit from the other side, the limit as x approaches 0 from the positive side of f of x, we're going to be choosing all of these values getting really close to 0, but from the positive side. And we're going to be going down this blue curve right here. And hopefully you can see we're not going to be approaching the y value of 0. We're going to be approaching the y value of 2 here. And even that's what our function is going to be defined at that point. So anyway, hopefully you can see that I guess our first condition of continuity hasn't been met, that these two limits are not equal. And so also, hopefully you can see that if we were going to take the overall limit, if we were going to say the limit as x approached 0 with no conditions, we're taking the two-sided limit of the function f of x as x approaches to 0. Hopefully you can see that because these two numbers are not equal, this two-sided limit does not exist. So DNE for does not exist. So this is going to be our jump discontinuity, and it fits with our definition of it fits with our definition of, I guess you could say it doesn't fit with our definition of continuity. We can see, or we can prove based on the definition of continuity, that this function is not continuous. So that is the jump discontinuity. I'm going to take just a couple of minutes. I'm going to show you one other example of a jump discontinuity. Just because typically when you see jump discontinuities, they really are going to be in this form. They're going to be in the piecewise definition of function form. But there is one other way that that you're going to see jump discontinuities shown probably in your calculus class. So I'm just going to go ahead and show you an example of that really quick. And that is, let's take another function. Let's take a function g of x. And we're going to define this function g of x as the absolute value of x minus 1 divided by x minus 1. And so now you might think that this looks really similar. This looks really similar to those functions that we looked at back when we did removable discontinuities, and even really similar to the function that we did in the very first video in this playlist, where you can say like, oh, well, this kind of looks like we're going to be canceling the two, and this is, this same something divided by that same something. This is probably going to simplify to some type of variable on 1. It's probably going to be just a line at 1 or a line at -1. And you would be right to think that. But one thing to just check out with this function, and let's just put in some values. And first off, let's realize one thing, that this function at x is equal to 1 is undefined. It's undefined at x is equal to 1. If we plug 1 into this, we're going to get 0. We're going to get the absolute value of 0 in the numerator, which is just 0. And then we're going to be dividing by 0 in the denominator. And we know that that is undefined. We can't do that. So therefore, we know that at x is equal to 1, this function is going to be undefined. So right there, we know that we don't have a continuous function. We're going to have some type of discontinuity here, because we can't just plug in any value for x and get a g of x value. We can't get a y value. So therefore, we know right off the bat that we're going to have some type of discontinuity. We just don't exactly know what kind of discontinuity it's going to be. So let's actually, from here, let's just draw up a table. If we were going to put in values of x along with different values for f of x, let's say we put in 0. Let's say we put in 0 for x. And so right here we would get 0 minus 1 in our denominator, or in our numerator, and we would get the absolute value of -1, which would just be 1. And we would divide that by 0 minus 1, which would just be -1. So we would get -1 there for x is equal to 0. So let me go ahead and plot that. So x is equal to 0, and our f of x of the function is going to be -1. Now let's put in, how about -1 here? So if we put in -1, you can see -1, that's going to be the absolute value of -2, which is 2. And then we're going to be dividing that by -1, which is -2. And you can see, again, we're going to get -1. So at the value of x is -1, we're going to get that point right there. And hopefully you can see, you can kind of extrapolate from that for all values less than x is equal to 1, our function is actually going to look like this. We're going to have a line at x is equal to -1, right up until we get to x is equal to 1, and then we're going to be undefined right there at that point. And actually, you know what? I've only got 30 seconds left before YouTube won't let me upload this video, so I'm going to stop here, and I'm going to continue this in the next video. So see you soon.